We're starting off with methods in algebra, and I'm going to start with the most mind-blowing piece of theory you've ever seen. Look at that. Like terms can be added or subtracted, unlike terms cannot. Basically, a pronumeral represents an unknown. We don't know what it is. But that doesn't stop us adding them or subtracting them. Like if I've got this unknown, and this is the same type of unknown, put them together, I know I've got two of them. I still don't know what they are, but I've got two of them. So anything that are alike, we can add and subtract. Unlike ones, we can't. That's the basic idea. I don't think I bothered with any examples on that. I think we've got that under control. I hope. Let's have a look at the index laws, how we manipulate when we're multiplying. And again, this should be like embedded in our heads, these ones. Multiplying, of course, we add the powers. Divide, we subtract the powers. When we have the parentheses situation, that's when we multiply the powers. So that becomes a dmn. Anything to the power of 0 is equal to 1, which is, of course, a lie, because that's not true. Come on, give me... All you need to prove something untrue is to give me one example where it doesn't work. Where doesn't it work? What number? 0, yeah. 0 to the power of 0. So no, 0 is a weird number. In fact, some people say it's not even a number. It's just a symbol used to represent the absence of value. Right? I mean, how do you write... Yeah, well, because how do you write down nothing? Oh, I'll leave it blank. But you're not really writing down nothing, you're just writing nothing. So we come up with this symbol for 0, and it has some weird properties. And so, yeah, 0 to the power of 0 is not actually equal to 1. And so that's the one counter example, I guess, of that idea of anything to the power of 0 is equal to 1. All right, but what do the indices or that index mean? They're like little instructions. And all right, we know that if it's a positive index, the message it says to me is, hey, I'm on the top of the fraction. Now, a lot of times that fraction is just over 1, so we don't write the fraction. But a positive index means, hey, I'm on the top of the fraction. The negative is the instruction that says, hey, I'm on the bottom of the fraction. So you see, x to the negative 2, you know, well, the x squared goes on the bottom of the fraction. I suppose more accurately, it means put me on the other side of the fraction. Because if you had something like 1 over x to the negative 2, then that would become x squared. Because the x to the negative 2 is on the bottom of the fraction, so you flip it to the other one and make it a positive. So it's a little instruction what to do with the pronumeral. And then you get these fractional powers. What do they mean? Well, the top of the fraction tells you the power, like normal. And the bottom of the fraction tells you the root. And how do I tend to remember that? Well, when I was first learning these, I think about a logical case, because I know x squared means x to the power of 2. And so if I think of it as a fraction, I would have written that as 2 over 1. So the top of the fraction tells me the power. The bottom of the fraction. So technically, I suppose, x squared is not just x to the power of 2. It's the first root of x to the power of 2. But, I mean, the first root is a really meaningless thing, so we don't really use it. We don't start roots until we say the second root, or as we more commonly call it, the square root. So when the bottom of the fraction is 2. So a over b would be the bth root of x to the power of a. Or alternatively, you could say it's the bth root of x all to the power of a. And so what that means is if you're using a number with this, it does not matter which order you do it in. Whether you do the power first, then find the root, or whether you do the root first, then find the power. You should get the same answer either way. So, all right, let's do some mind-blowing examples here. X to the negative 3. Get rid of... negative sign. That's an instruction. I'm on the bottom of the fraction, so 1 over x cubed. And then we try and make them look a bit trickier. It's got both positive and negative. What do we do there? Positive goes to the top of the fraction. Negative goes to the bottom of the fraction. A to the power of 5 over b to the power of 7. What's he doing now? But again, see, this is what we love to do, maths. You ever notice that in maths tests? We're just trying to make questions look harder. They're not really harder. You just got to apply the same rules each and every time. 3/4 has already been done for us. 3's on top, 4's on bottom. So brilliant. But then the x to the negative 4, so that's on the bottom, x to the 4. Positive 9's on top, b to the negative b squared goes on bottom. x to the power of a quarter, then now we're talking about the roots. So that's the fourth root of x to the power of 1, but we don't normally write power of 1, of course. Y to the power of 2/3, the cube root of y squared. I tend to write them this way rather than the other format, but as I say, either is correct. Other way around, you get x to the power of 3 on 2. That would become the square root of x cubed. But I'm sure you're even saying it to yourself now, even as I speak. Oh, hang on. That surd can be simplified. We're very good at simplifying surds when they're numbers. Algebra, we go, oh, hang on a sec. Why would we do that? Well, you always do it when it's numbers. Why wouldn't you do it when it's algebra as well? How do you tell? Well, how you tell is the fraction. If it's an improper fraction, that surd will be able to be simplified. Okay? So 3 on 2 is an improper fraction. Well, what would it be? Well, what do you do when you're simplifying surds? You're trying to find a perfect square times that, so you can say the square root of the perfect square. Well, x cubed, I can make that a perfect square times something. I can make it x squared times x. And the square root of x squared is x. So it becomes x root x. Now, in reality, that's not how I would do that question, but that's the idea behind it. It's quicker if you pick up that idea about the improper fraction. So you got 3 on 2. You see the 3 on 2. But you think 1.5. You never write x to the power of 1.5. That's just bad maths. All right? So I'm seeing 3 on 2, but in my head, I'm seeing 1.5, and I've got the answer straight away. X to the power of 1 times x to the power of 1/2. So x root x. There's the answer. Okay. Whoop, x to the power of 1 and x to the power of 1/2. So now we can make it look harder. M to the power of 27 on 4. Not that I think we'll ever get a question like that, but anyway, the same theory applies. 27 on 4, oh, that's an improper fraction. That's 6 and 3. Oh, very good, very good. 6 3/4. So it's m to the power of 6 and m to the power of 3/4, but m to the power of 3/4 would be the fourth root of m cubed. Right? So it's all the same basic idea. We just make the question look harder. So you get something like this. Oh, geez. Someone's having a day. Okay, half n to the power of minus 6, p to the power of 500, q to the power of minus 1 on 28, c to the power of 7 on 6, and r to the power of 69. Okay, let's draw in a, what's that called, by the way? Anyone there? Thank you. It's a vinculum. That is the actual name for fraction bar. Most of you probably went, fraction bar? Vinculum is the actual technically. Don't worry, that won't be in the test. Okay. So let's sort this out. Half, what's already been done for me. 1's on the top, 2's on the bottom. I don't usually write 1 when I'm dealing with algebra, so unless there's nothing else there, so we'll wait and see what happens. N to the power of negative 6, oh, well, that's on the bottom. P to the 500, oh, that's on top. Negative 1 on 28. But 1 on 28 would, of course, mean the 28th root of q, and it's on the bottom. C to the power of 7 on 6. Oh, hang on a sec. 7 on 6, that's an improper fraction. 7 on 6 is 1 and 1/6. So it's c to the power of 1 times c to the power of 1/6. And c to the power of 1/6 would be the 6th root of c. And then we just got our last one there. There it is, r to the power of 69. Voila, a thing of beauty. What mere mortals would shudder at in fear when they see the question, we now just look at it and go, ha, piece of cake. Well, let's hope so. Fractions to negative powers are always interesting. Because remember I said the other way you could think about negative indices is, hey, actually I'm on the other side of the fraction. So you see a fraction to a negative power, change it to a positive power. Makes it easier. Because that negative instruction is saying, hey, I'm on the other side of the fraction. So the 2 was on the top, is now on the bottom. 3 was on the bottom, is now on the top. 3 on 2 squared, oh, well, that's easy. That's 9 on 4. Okay? So use the instruction, use the negative. Okay, I've talked enough, I think. Lots of fun ahead. exercise 1A. Oh, 6A, I've jumped ahead a bit there. I think there's some questions there as well.